All right. Good afternoon, everyone, and welcome to our webinar. Sorry, a little technical difficulty. Forgot I had my mic muted there, but John Ricco, Executive Director. And so we've got Managing Air and Concrete is our webinar topic today. And before I jump in and introduce our speaker, I'm going to just give a few housekeeping things. If you have any questions as we go through the webinar, feel free to submit them. If you are logged into a YouTube account, you'll be able to just do that in the chat feature on the right-hand column of your screen. If not, intermittently throughout the webinar, an email address will pop up through on the bottom of your screen, and you'll be able to send questions to that email account. So that's kind of some of the housekeeping stuff. Just a couple of other things to touch on to make sure you're aware of. The APA has a UHPC workshop that we're working on for April 4th through 6th in Tacoma, Washington. So we hope to see you out there. If you're interested in learning more about UHPC, we'll actually be doing some hands-on stuff in Tim McGordy's plant out there at Northwest Precast. So we would encourage you to take a look at that, and information will be coming forth on that on the website in the very near future. Just to save the date type of piece here, our 2024 annual convention will be in Park City, Utah at the end of October. So please put that on your calendar as well. In terms of other upcoming Lunch and Learn webinars, our last one of the year will be on November 15th at lunchtime Eastern time, and Dave Ellis with NAWCA will be presenting on concrete staining, and so that should be a great, excellent webinar for our members as well. I always like to point out that we have a few great membership benefits for those of you that are APA certified plants. Office supply discount savings through ODP, which is Office Depot's online business-to-business portal, as well as shipping through UPS. So I'd encourage you to check those out if you're looking to reduce your costs on office supplies. Obviously, we're all over the place in terms of social media, on Facebook, Twitter, Instagram, you name it. What's going on in the plant have proven to be a really popular weekly posts where we just kind of shine a light on what's going on with our plants throughout the country and the neat projects that they're working on. So I'd encourage you to check that out. And if you're an APA plant, go ahead and send some photos and a brief description on any cool projects you might be working on. And so that I'm going to go ahead and pull that out of there. And we are going to pull this up, and we are going to introduce our presenter today, Terry Harris. So Terry is Director of Technical and Engineering Services with GCP Applied Technologies. He started in the concrete industry in 1979 and has joined more than 43 years of experience with ready mix, with precast, masonry, and admixtures. He's an active participant in ACI, ASTM, NRMCA, and PCA, ACPA, RCC Council, the ACI Strategic Development Council, and the RMC Foundation Advisory Council, a lot of letters and acronyms there. Terry is a past chair of the ACI Certification Committee. He's on the Fellows Nominating Committee for ACI, and he's the current chair of the ASTM and ACI committees on admixtures, among many others. He's a very active and engaged guy. He has a degree in concrete technology from Daytona State College, and he is also an ACI fellow. So with that, Terry, I welcome you. I thank you for being here today and looking forward to hearing your presentation.
Thanks. I appreciate it. I'm happy to be here.
Yeah, we'll let you go ahead and get started with the webinar. Thank you.
Thank you. Okay, so a couple things right off the bat. Managing air and concrete, or controlling air and concrete, is a bit of a misnomer. It's probably the hardest thing to control because we can't really get a grip on what it is at the plant or at the form until we actually get it there. So really more difficult than slump or any of the other attributes we're looking at to control. And for the architectural precast guys, it's even a step up from that because you guys don't always use aggregates that are friendly with entraining air and concrete. You use aggregates for aesthetics, to get a certain look, to meet the owner of the project happy, and they don't always make it easy to get or keep air in the concrete. So I wanted to throw that out right off the bat that you guys have your work cut out for you, and I appreciate that. So managing air and concrete, as you guys know, concrete's an amazing product. It can be formed into almost anything. And I've been promising my wife for years that we were going to have concrete countertops, and I still haven't done that yet. So I'm sure I'll get reminded of that again. So it's an amazing product, amazing material. We can do a lot with it. And part of that is to make it durable, right? So why do we want air and train concrete? It's for durability. So how do we get that? Well, we have to start with good aggregates. And again, good doesn't necessarily mean good for entraining air. Durable aggregates is maybe a better word to use. We're going to have powder, cement, and a number of other pozzolans that could be available. And we're seeing more of those on the market. Some of you may have gone to 1L Cement recently, and that's offered some other challenges with entraining air and keeping air. And then we have the water, of course, and then, of course, our source of surfactants. We don't use Joy dishwashing liquid, but they are similar families. So one thing about air entrainment, it's not a foaming agent. If you put air entrainment into your concrete, you're not getting air until you mix that concrete. And we're going to talk a little bit about mixers and how they impact the air. But if we don't mix it, we're not getting it. Just like when you wash the dishes at home, you put the Joy into the sink with water. And until you get some agitation, until you stir the water, you don't get the foam. It's the same with air entrainment. You have to have mixing. So there are a number of different mixers that we can use. Some of you guys use the drum mixers, which are stationary. Some use ready mix trucks to move the concrete out to the forms. We have planetary mixers. We have pan mixers. We have these ribbon mixers. I don't see as much of these anymore as I used to. We have the single shaft and the twin shaft mixers. And all of these will take the same materials, same amounts of material, same amount of air entraining agent, and give you different air contents. And that's just because the mixing action is different. For example, it would typically take more air in a pan mixer to get the air you need than it would in a twin shaft mixer or a drum mixer, just because the mixing action is different. So if you change mixers, be prepared to do some testing with the air. If you get a new mixer, get a new liner, install new blades. Any of those things are going to impact the air. If you have buildup on the mixer, if you have, again, worn blades, if you have gaps between the blades and the body of the mixer, all those things are going to play a huge role in how much air you get and how long it takes to get there. So air entraining agents, they're pretty simple materials, right? They really do one thing, and that's take the bubbles that are created when you're mixing the concrete, and they turn those bubbles, those bigger bubbles, into well-spaced small bubbles. And the reason they do that is you have one end of that surfactant that likes water, and you have another end that doesn't like water. So what happens is you get the tail sticking into the air, the head of that sticking into the water, and then you goes on that, and that makes that bubble much tougher than the bubble that would be there without the mixing. So when you mix concrete, you're always generating some air. That air is mostly going to go away as soon as you stop mixing. When you put the air entrainment in there, it stabilizes those bubbles that are created during mixing, and they don't go away. Now, some of them will obviously dissipate over time. The bigger bubbles will tend to come out quickly, and we're going to talk about that a little more later. So then you'll see, again, we're getting more of these molecules around this bubble. We're getting more bubbles. And I'm going to go through this fairly quickly. And then you'll see that you'll get the aggregate. You have the cement. sorry. And then you've got the water, you've got all these materials, and air needs a really stable home life. So for air to survive, for the air to build and then to stay stable, it needs a stable home life. And we'll talk more about individual agreement materials later, but that whole mortar phase of the mix, that material passing the number 8, that's where the air lives, and in particular those areas between the 30 and the 100 sieve. So we need that material in there to give that air a stable place to live. The other thing that impacts that, again, that we'll talk about later, is the rheology of this mix. And I'm sure some of you are doing self-consolidating concrete, and that presents its own set of challenges. Okay, so benefits of air, obviously workability is a side benefit of that. You can get less segregation and less bleeding with air because those channels are now disconnected because you've got the air bubbles in between, so that water's got to work harder to bleed out. You do get better finishability with low powder content mixes. If you have high powder content mixes, a lot of air can cause it to behave a little bit sticky. Of course, we get more yield out of the same batch of concrete when you have air in it. And then the main reason we use air is for freeze-thaw durability. Okay, so concrete is a great product, as we mentioned. However, it is a sponge. It is not waterproof unless you do something to make it so. And it's also weak in tensile strength. So we have a material that will absorb water, allow water in. It's weak in tensile strength. And then, as we all know, water expands when it freezes, and it expands about 9%. So it's going to grow, and the outward force is at about 10,000 PSI. So it's a lot of force. And again, that's internal, so it's tensile. So our concrete is not able to withstand that. So the concrete gets wet. It can take it for a little while, but after repeated cycles of freezing and thawing, it will fail if it's not properly air entrained. And there's some other things that go into freeze-thaw durability that we're not going to spend a lot of time on here today. So here's what happens. I have a no air mix. I don't have any air voids in here. You have the hardened concrete. I have water get in here. Now down below that, I have these capillaries full of water, and they are freezing. And you can see that in this illustration, I'm starting to get some cracking. Usually we see this on the surface of the concrete. We don't necessarily see the cracking. What we see is the top coming off, but the cracking is where that starts because we're exerting this internal pressure on this system that can handle it. So what happens in a air entrained mix? Well, these voids, they have that coating on them from the solution of the air entrainment mixing with the water and the cement. So it makes them a bit resistant to water penetration. So what happens? They are empty. All the capillaries are full. Then that water starts to freeze and expand, and it pushes itself out into these air voids. And that's how we get the protection from those cracks that you see over here, and they don't occur over here. This is just some really bad pictures of freeze thaw. Now, you will occasionally see something like this cracking in the bottom right hand, but mostly what we see is the concrete starting to deteriorate. And usually that's on the surface, and these are some freeze thaw beams. That one obviously is failing, and the other one has passed. And if you're not familiar with the testing for this, it's ASTM C666, and you can look that up. Again, air entrainment's been around since the 1930s, discovered accidentally by a forerunner to the GCP business in Cambridge, Mass. Okay, air entrainment. Now this is This is out of ACI. You will see not just this specification, but engineers will write their own specifications, and it may or may not coincide with this. But essentially, as you get lower in aggregate size, you're going to need more air for protection. And it's not just the percentage of air, it's the size of the air, and we're going to get into that as well. Yeah, so C666, it is a very severe test, but it is the only test we have. It takes about 90 days to run it because you're cycling through 300 cycles of freezing and thawing. And what you'll see is, again, air content's low. You're almost always going to pass freeze thaw. However, with some very good concrete mixes and some very good air systems, we can see good passing or good durable concrete at 3%. We've seen some of that. Again, very low water cement ratio mixes with some very good 3% air can survive that. Okay. Don't see that often. Typically what we're looking for is, again, up in that 4+% with low water cement ratio as well. Test for air entrainment. Now, I'm going to get on a hobby horse here for a bit. The chase indicator is not a test. However, if you are having difficulty having consistent air entrainment, it is a good tool to use to do a quick test on each batch that you make. Very simple test to run. It will give you an indication of what the air is. Obviously, you're only testing the mortar in this test. So it's not going to give you as accurate of a reading as the rollometer or the pressure meter, but it is a really good test to run. And this only tells you the air content. It doesn't tell you the whether it's a large bubble or a small bubble. The other thing I would suggest is that anytime you're doing any testing is run the unit weight. If you have the air content and the unit weight, you can learn a lot about your mix, whether you're having trouble with air or not. So it's my suggestion that you always run unit weight when you're testing concrete. Okay, so air voids. So if we have a basketball and we need 7% air, and a basketball, the air volume is about 0.25 cubic feet. Okay, so in this example, if I need 7% air, then I can put about 8 basketballs into the concrete, right? So I would have 7% air in a yard of concrete. Now, first of all, it'd be a silly idea. Secondly, all these would be way too big to offer any protection for the concrete. So just to give you an idea of how much air we're talking about, that's what this looks like. So what we need to do is to take these big bubbles and change them into small bubbles. And that's what the air entrain materials do. Taking these big bubbles that are generated when we mix the concrete, turning them into lots of very small bubbles. So just a quick note, when you're doing hardened air, the polish is key to getting good results. So if you're getting a polish on your concrete where it shows the air voids that are raveling or ragged edges, you're not going to get an appropriate reading on the air void. That's just a side note. So here you can see the different sized entrained air, and this is obviously magnified. And then you'll see these irregular shaped bubbles that are entrapped air. And when we count air, when we do a hardened air test, we're counting all of those voids, not just the entrained bubbles, but all of those bubbles. Okay, so how far can the water travel? Well, the answer is not very far. It's about the thickness of this 10 mil poly, right? So that's what we're looking at. That's why we need the bubbles to be close together, and we need them to be small so that they can be close together, fill each one of them as the ice starts to grow inside the concrete. And that's what keeps us from having problems with our concrete. Spacing factor, again, typically less than the 0.008 is the number that we see specified if air void is specified. And that's basically half the distance between the two air voids is what the 0.008 represents. So not very far. I apologize. Sometimes the slide advances and sometimes it doesn't want to. Okay, so here we have these air voids again, and we're looking at some that are spaced out, not as much as we'd like. So we want to measure these, and the way we measure these is with a microscope is the traditional way to do this, ASTM C457. And linear traverse just means that someone is reading this line and it's bubble on, bubble off when they see a bubble. So they're using that to both count the number of bubbles or the percentage of air, the spacing factor of the bubbles, and the size of the bubbles. Now, fortunately, we can do that in a different way now. We can use a computer to do this. So we do the same polish. We blacken the surface, fill the voids with a white powder, and then we put that under a computer with a camera, and it does the reading for us. So you can see here the different size bubbles in white. And again, some of them are entrapped, some are entrained, and the very small bubbles that you see in here. Now, it may be hard for us to pick these up, but the computer does a really good job of doing that. We get much more consistent results with this test. Void frequency, that's how often the voids occur. Again, specific surface is the indication of the bubble size, and then the void chord length is the diameter of the bubbles. So here we're just seeing a distribution of those bubbles, and the ones that are down here on the very small end is what we're looking for to get us very good freestyle protection. In reality, we can get over this 010 and still have good freestyle protection, but we're going to need more bubbles to do that. And this is a just an example, really, of different readings with different air entrainments at different water cement ratios. So same mix, different materials, and we're getting different results. And again, you can see that spacing factor often goes along with how much air we get. So the more air we get, we tend to get smaller bubbles. Okay, so what in the world do we do to control this air in our concrete? Well, so a couple things that we need to think about. One is, again, all these materials that go into the mix. The more consistent our materials going into the mix, the better the control is going to be of the air. The one key, if I could say there is one key to controlling or managing air in a consistent way, is that the materials going into the concrete are consistent. So what do I mean by that? So for example, if you're changing cement sources on a regular basis, you're going to struggle with controlling your air. Within the cement, there are some things that we'll talk about in a bit that you can monitor to tell you if you're going to struggle with air or not struggle with air. Slump needs to be consistent. Mixing time needs to be consistent. If you are using mixer trucks to deliver the concrete, how fast that drum is turning needs to be consistent. Consistency in everything we do, from the materials we use to the practices we have, that's the key to doing that. So the other thing is the rheology of the mix. Now, we can have a 7-inch slump that's easy to move, has the right amount of water and admixture combination in it, or we can have a 7-inch slump that's really hard to move, kind of like the Play-Doh here. There, it holds its shape, doesn't move. We've got to use some energy to make it move. So not every 7-inch slump is the same. The same with SEC. We can have a 25-inch slump flow that gets to a 25-inch in just a matter of seconds, or we can have a 25-inch slump flow that you can take a break, go get a cup of coffee, come back, and it's still creeping out to 25 inches. So the materials, the rheology of the mix, and your production process, those are the keys, and doing those consistently, those are the keys to getting the concrete to turn out. And I know what you're thinking, right? Easy to say, hard to do. Totally agree with that. So looking at the materials, and we'll jump ahead. If someone asks me what in the mix affects air, and I'm sure if you've been in the concrete industry more than a minute, you know that everything, literally everything in the mix can affect the air entrainment. So if you go up on the cement content, you likely will need to increase your air entraining agent. If you change the source, you're likely going to need to change, adjust your air entraining agent. If you increase the fineness, you will likely need more air entrainment. One thing we saw with some of the 1L cements is as they switched from 1.2 to 1L, they got finer. So the fineness went up. A lot of that was the limestone portion being fine, but still we saw that it was a bit more difficult to get air in some of those cases because of the fineness. Some of that was due to the fact that the water demand went up. And so as the water demand went up, we were using more admixture, less water, hard to get air entrainment. Okay, so one thing you can certainly look at, or two things you can look at on a MilCert. One is the blane, see how fine it is. You can also look at the 315. If the blane's changing and the 315 is not changing, then there could be something going on there with really fine particles. And then the alkalis. The higher the alkali of a given source of cement, the easier it is to entrain air. So if I have a source of cement and my alkali is at 0.4, a month later it's up to 0.6 or 0.7, it's going to be a lot easier to get air into that concrete. So that's one of the things to look out for. And then I get asked this question often: what if I just get in a delivery of cement? Sometimes it seems like that causes my air to go haywire. It can happen. Any of those things that I just mentioned can be changing with a new load of cement. The other thing is the temperature can be when the mills are running at capacity. You may be getting cement that's not sitting in a silo for any length of time, and the temperature could be a bit higher. And if the temperature is higher, it's going to cause you to need more air in the concrete. We had a customer some years ago now that was getting cement. They were already in the hot weather market, and we ended up putting about 5 gallons of air in a 3-yard batch at a precast plant to get air. And it was just because the cement was coming in at a fairly high temperature, which 5 gallons of air, that falls under the category of that would scare the crap out of you to use that much air in your concrete. If things go back the other way, you're going to have a lot of air. So yes, when you're chasing air issues, when you're trying to control air, anything that's different should be noted. Okay, fly ash, and I know that in architectural plants, it's not always used. There are some that do that, but fly ash typically causes the air entrainment dosage to be increased. That can be because of the fineness. It can be because of the LOI. So if you have a higher LOI, or if you have a fluctuating LOI, it can be a real challenge to get consistent air. So the LOI, the carbon in the fly ash, will act as a sponge and absorb that air entraining agent. And so it's not available to help stabilize those bubbles. So the higher that number is, the more difficult it is to get consistent air. The type F ashes do tend to have a higher AEA demand, and that's typically because they have a higher LOI for the most part than the type Cs. And you can use the foam index test as a quality tool to check your incoming fly ash samples. It's a very easy test to run, doesn't require a lot of training. And if anybody's interested in that, you could email me at any time and I can send you how to do that. But it is something that's doable. We also see treated ashes, and some of them are double treated. What I mean by that is some of them have activated carbon added for mercury abatement, and then a surfactant is added on top of that to offset that activated carbon. And we also see some of the fly ashes that just in general have carbon, high carbon. Those are also treated with a surfactant to make it easier to get air. My personal opinion is I would rather deal with a high carbon and increase my dosage of air entrainment than have it treated. That's just my opinion. Silica fume. Now, typically, it does cause your air entrainment dosage to go up. However, in some cases where you're using silica fume in a self-consolidating concrete mix, and you have a mix that is on the edge of segregation, so it's good. It's not segregating, but it's almost there. Those can be difficult to maintain air content. So you can get the air, but it comes out pretty quickly. And some of those mixes, if you use silica fume, it stabilizes that, stops that segregation, and actually will bring your air entrainment dosage down. It's not typically what happens, but again, if the silica fume is making that mix more cohesive, remember we talked about needing a stable home life for the air bubbles. That's what we mean by that. That we don't need the mix to be excessively bleeding. And I know that's a terrible choice of words, because what is excessive? I can't define it, but I know it when I see it. Then those mixes are going to have a hard time keeping air in the mix. And that's why sometimes with architectural concrete, we're using aggregates that are not friendly with air, and we struggle to control the air with those mixes. Okay, aggregates. Not all rocks are the same. And yeah, I know it's a bad pun, but it's the best one I had. So they're not all the same. So again, consistency in your aggregates and managing your stockpiles is key. If you have a loader operator and he is managing the stockpile, someone that's doing a really good job can make life much easier with getting air than someone that's not. So backstacking your stockpiles, not digging too low in the stockpile, not digging in one spot for the entire day, because then you tend to start segregating the stockpiles. So what we want is we want a consistent gradation delivered to the batch plant. And while sometimes we have consistent gradations delivered to our stockpiles, our handling practices make it difficult to keep that consistent going from the stockpile to the batch plant. So we want that to be consistent. Cleanliness. If again, the guy that's managing those stockpiles can pay attention, note any clay balls or any coatings on the aggregate as those are happening, and you see a change, you're almost always going to see your air entrainment dosage increase because of those fine materials. And you likely will also see an increase in water demand so you're going to get hit with a double whammy with doing that. So paying attention to those stockpiles, making sure that they're consistent in gradation, making sure that they're clean, definitely going to make a big impact on your ability to control the air. And then rounded aggregates are going to be easier to entrain air than angular aggregates. And this is a really good picture here on the screen of the difference between the two. Typically, water demands less. Typically, it moves easier, so you don't need all the water and everything. And so it's just easier to create those air voids that we're looking for. So for the coarse aggregate, again, moving from a larger stone to a smaller stone, I'm gonna need less air entrainment, higher air for protection, right? Easier to get air with smaller stone. I'm gonna need less air entrainment with rounded stone, and if I can be consistent and the material that I'm actually putting in the plant, and it would be a good idea to conduct plant audits. If you're not familiar with what that looks like, again, I'm happy to help with that. But plant audits to make sure that each step of the process is being handled consistently, it's going to make a big difference in your ability to control the air consistently. Fine aggregate, and this is really, if I had to say which material can I control to make the biggest impact on the air, I would say if you're dealing with a decent fly ash, it's going to be the sand. If you have a crappy fly ash that the carbon's all over the place, then it's going to be the fly ash. In either case, a consistent sand gradation is going to be a huge help. Now, yes, if you're using natural sand, easier to get air than it is with manufactured sand. But in both cases, if you can have consistent gradations, that is the key to having the right air entrainment. Now, you can use the FM of your sand as a tool to track consistency of the material, but you can't just look at that alone. You're going to have to be able to look at each sieve size and make sure that it's being consistent. And what you will likely find is that you need a much tighter range of control than what ASTM allows. So, for instance, one sieve in ASTM has a 10 to 30 range. That's a huge range. So if you're at 10, you're going to struggle to get there. If you're at 30, and this is the 50 sieve, then you're going to have no issue getting air. A number of customers that I work with, they've worked with their aggregate supplier to say, I know what ASTM says, I know what the DOT says, but I need this range. And in one case, we've got one customer that because of the type of concrete he places in his precast plant, it's not just about air, it's about stability, and he has a minimum of 15% passing that 50 sieve because his what he's doing is just not going to work if he gets less sand than that. So again, the 30, the 50, the 100, and I would tell you especially the 50 and 100 sieve, that's where you need consistent material to be able to produce consistent air. The amount of sand in the mix is also going to impact that, and we'll talk about that in a bit. Again, that material passing the 200 sieve, it may not be clay or silt, but tracking that, doing a sand equivalent or some other test that shows you what that material is going to be key to track any changes with that. If you don't have a program where you're doing some in-house quality checks on your sand gradations and your stone gradations, then I would strongly suggest that you start doing that. And again, I think with enough testing and correlating that with your air contents and your ability to get air and keep air, that's going to tell you where that window is that you can work in successfully. Again, I realize that aggregate choice for you guys is often not about air; it's about something else. We've covered this. Okay, just a real quick picture here of as you go up on the sand content, your air is going to go up. So the more sand you use, the higher the air content will be because you have more of a home for the air to live in. Now, again, most of your mixes are probably based on the amount of sand and stone you need to acquire a look. But again, if you're struggling to get air, if you can put a little more sand in the mix, and we see this not just in precast, but in ready mix as well, especially with higher strength mixes, sand content tends to be low. We bump the sand a little bit. We make that adjustment, and we see that we can get sand much easier. We can get air much easier and much more consistently. When I make adjustments, when I'm testing, I make 1 cubic foot adjustments, which is about 100 pounds of sand. So if I think not enough sand is in the mix, I'll increase it 100 pounds, see if I move the needle at all. Making small changes, you may not see a change. So you make a big change, and then if it's too much sand for the look you're trying to get, you can back that down to 50 pounds and see if you get the same impact there. The amount of sand is definitely going to make a big impact on how easy or hard it is to get air and how much air you're going to get. Okay, water needs to be potable, which means, if you don't drink it, you may not want to use it. There are a lot of producers that use recycled water, wash water, those kind of things. We actually have some producers that are drawing water out of a canal, and they can do that successfully as long as it's consistent. Now, there are some things, if you're collecting water in your plant, and you've got oils and stuff running off into the water, and that can wreak havoc one way or the other with your air entrainment. So again, like all the other ingredients that we're talking about, being consistent with the water is the key, and not just the makeup of the water, the composition of the water, but how much water I'm using in the mix. Okay, admixtures, my favorite subject. So all of these products are going to have an impact on air. Obviously, the air entraining admixtures, but water reducers, retarders, high range water reducers, accelerators, corrosion inhibitors, all of these are going to have an impact on the amount of air that we get. So I'm going to jump into this. I'm going to struggle to finish all of these, so I'm going to go through some of this quicker than others. And again, if you have questions, hopefully I can pick those up. So there are different chemistries. Vinzol resin, the original air entrainment, doesn't need as much mixing, gives you a decent bubble. Tall oils give you a smaller, tougher bubble, and take a little longer to mix. And one is not necessarily better than the other, but they do behave differently as far as getting to the air you're looking for. So they're chemically different, do the same things. One's going to need more mixing than the other. Water reducers, if you're using a lignin-based water reducer, your air entrainment requirement is going to go down. Lignins can entrain some air on their own, typically not great air, but if you're using a lignin-based water reducer, they will certainly reduce the amount of air entrainment that you need. Some of the sugars, carbohydrates, they may reduce it, but may not. And then the um, uh, gluconates tend to be minimal impact on that. Calcium chloride can cause you to increase slightly. I don't know that you guys would use a lot of calcium chloride, but they typically don't have a big impact. Now, non-chloride accelerators, yes, typically it's a minimal impact, but if you're using hot water, non-chloride accelerators, and you're trying to get air entrainment, you can struggle. And a lot of that's going to come down to dosing sequence. And dosing sequence makes a difference in general, but when you're doing hot water and non-chloride accelerators, you really can have a huge impact on the air. So we don't want those all going in at the same time. We prefer to see the air entrainment dosed onto the sand. We realize that's not always possible, but if you're using hot water, you're using non-chloride, then you want to keep those separate from when the air goes in. And the best sequence, we internally have a recommended sequence of how the products go in, but it doesn't work for everyone because plants are all different, mixers are all different, how the materials delivered to the mixer is different. So we try to work with our customers to help them determine the best material sequencing that will give them the most consistent air. High range water reducers, not a lot of naphthalines and melamines around anymore. They don't impact it too much unless you get the concrete too fluid, and then you're not going to be able to keep the air in there. Polycarboxylate based high range water reducers all have defoamers in them. They're all different. Typically, you will need less air entrainment when you're using a polycarboxylate admixture, which is probably 99% of the high range water reducers on the market are polycarboxylate today. Corrosion inhibitors, like accelerators, they can impact it slightly. And again, if you're using a corrosion inhibitor with a hot water, that can be an issue. Shrinkage reducing admixtures, that can be a bit all over the place. Some of them you cannot get air with, so you would have to be very selective of the shrinkage reducing admixture that you're going to use, and then test to make sure you can get it. And again, don't put the air in the same time the shrinkage reducer is going in. Viscosity modifiers can be your friend if you're struggling to get air, especially if you're placing high slump mixes or high flow mixes, and you're having what I would say is a bit of a witch's brew. So you place the concrete in the forms, or you place it in a bucket to deliver it, or it's you see it in the truck and you get that bubbling cauldron effect. Doesn't necessarily mean all the air is coming out, but it does mean that mix is struggling to maintain its stability. And you will see those mixes tend to be much more difficult to keep the air. So the viscosity modifiers can stabilize that home life area and make it easier for the bubbles to develop and to keep the bubbles in there. And this is where the rheology comes into play. So we can increase the viscosity of the mix enough so that we can keep the air bubbles in that we're trying to entrain, but not to the point where the mix becomes sticky, gooey, hard to manage, doesn't flow, those kind of things. So it's a balancing act, but we've been very successful using viscosity modifiers to make it easier to get air, especially in mixes where we can't get enough sand in the mix for whatever reason. Just makes it much easier to get that air and to get it stabilized. Pigments, you're going to be all over the board with pigments. Some of them are not going to impact very much, and some of them will impact significantly. Carbon black, obviously, if you're using that, is going to require a significant increase in air entrainment. For the other products on the market, some of them are much less impact than others. So I would just say that you're going to need to do a lot of testing with colors to find out the right sequence of materials and the dosage that you need to get the air that you're looking for. Okay, so again, all of these materials can have an impact on air. Having consistent materials, having a consistent batching sequence, having a consistent mixing time, that's going to be the key. I should have touched on this earlier. I know sometimes in precast we start the mixer and then we end up waiting for the bucket or waiting for the truck or the tucker or whatever our transportation is, and so we keep that concrete mixing. Many times I'm either going to cause the air to go up or go down by that extended mixing. So the same mixing time, the same sequence, consistent materials, consistent workability levels, both from the rheology aspect and from the slump or slump flow aspect, is going to be huge in getting consistent materials. Production, I've been talking about that. Batch size is another thing to consider. If I'm consistently doing 4-yard batches and then I switch to a 2-yard batch, my air content is likely going to go up because I'm getting more efficient mixing. We've talked about most of these other things, but placing in vibration, if you're required to do in place hardened air, that's obviously going to make a big difference, right? So doing that in the right manner, and we could do a whole presentation on the proper way to vibrate concrete, which we won't get into here, but throwing it out, fishing, pulling it back, getting too close to the forms, all those things are bad ideas. And I'm sure you guys know that because it's not helpful for the appearance of your concrete either. Sampling and testing. So this is a really bad picture of somebody taking a sample because dropping it like that is going to change the impact or change the air. Getting representative samples. If you're sampling from a truck, I always suggest that you throw out the first half wheelbarrow or so and get the next one, because that tail end may have more rock. It may have more water. It doesn't always mix consistently. So taking appropriate samples and then mixing those samples is a good thing. Now, I have seen someone get a sample at the bed and then put it in the back of a gator and drive half a mile to the lab and bounce that all over the place. You're not going to get the same air content. It's just not going to happen. So, sampling it, not letting it drop, getting it as close to where you're going to run the test as possible is going to give you much more consistent results. Again, another bad picture that doesn't have anything to do with precast. It's just a really bad picture of guys testing inappropriately. Excuse me. Make sure your air meter's calibrated, and I would do that more often than they recommend, just because we work in very difficult environments, and we can lose our calibration very easily. Strike off bar, but not when you're doing unit weight. And I know that this happens all the time. I think we get some bad numbers on unit weights, and we want to be able to correlate that unit weight with our air content and make sure that we're getting the right numbers. Again, I would always run unit weight no matter what I'm testing for. Otherwise, I would test for unit weight. And yes, if the unit weight goes down, there's only two things that will make it lighter, and it's air or water. So if I'm checking the air and I'm checking the unit weight and those two don't match up, if the unit weight is lighter than it should be, then chances are I've got too much water in the mix. And I know that's hard to tell sometimes if we're using the right amount of water, but anyway, it's a good test to run and to correlate those two things. And this is just an example of unit weight correlation. We've also got strength on here. And one thing I'll point out is we talk about losing 5% of our strength for each percent increase in air. Our experience is that when you get over 7%, that number changes dramatically. So if you're fine with 7% on strength and you go to 8% or 9%, you're going to see a huge drop in strength. So it's not a linear loss of strength from 3 to 6 or 7%, pretty linear. Once you get over that number, it's going to go up significantly. Scales are cheap. I know that I've visited a lot of plants, and I don't see unit weight run as often as I'd like. So it's a really good tool, and I won't hammer on that anymore. I think we've covered that. Yeah, so sampling from a truck, as I mentioned, the speed the drum's turning, how much it's turning, those kind of things are important. So you don't need to spin it at the entire speed, so charging speed. So 10 to 12 revolutions per minute is ideal for those drum mixers to give the air that we're looking for. Again, we talked about this. If I'm doing less than full loads, I'm going to get more air than if I'm doing full loads, or 4 yards versus 2 yards, 6 yards versus 3 yards. It's going to change. And John, am I running out of time?
Well, yeah, you're getting close. You got about 3 to 4 minutes left.
Okay, thank you. I'm going to skip ahead to just a couple of slides that I wanted to cover here. And by the way, I'm famous for never finishing a presentation, so my reputation is intact. So just wanted to talk real quick about the bubbles, right? So we talked about big bubbles, small bubbles, and then that rheology of the mix. So mixes that, again, are unstable, they're watery, you pull a slump, you can see some water or paste running away. Those are going to make it very difficult to keep the bubbles in. The bigger the bubble, the easier it is for them to come to the surface. So not all the bubbles leaving are necessarily a bad thing, but those big bubbles leaving are. And if you think about viscosity, and I'll stop here, John. We have water on the left, you have corn syrup, oil, and then honey. If you create bubbles in the water, very easy for those bubbles to travel to the surface. The corn syrup going to be less so. And then all the way over to honey. Now, if we get to the concrete with consistency of honey, it's going to be hard to move. It's going to be not very flowable, going to be sticky, but the bubbles are going to stay in that mix very easily. So again, we want to be somewhere in this corn syrup to oil viscosity, not water, not honey, but we want to have the right viscosity to make it easier to keep the bubbles in the mix and still be able to move the concrete. And again, those viscosity modifiers can take us from this water consistency to the corn syrup or maybe oil consistency. And John, I'll stop there and see if there's any questions out there.
Yeah, we do have a couple. One that popped up here on the YouTube channel. It says, how does admix that controls efflorescence react with air entrainment? That's
a good question. Typically, again, you would want to keep those materials added separately. But if the mix is a good mix, we typically don't see a big impact on those efflorescence control admixtures impacting air content.
All right, very good. And the other one that came in through email, we've been talking a lot about UHPC lately, so that's probably what prompted this. But how does air entrainment affect, or how is applicable with UHPC? That's the question.
Yeah. So you typically don't want air in UHPC. We've worked with a number of producers to develop mixes. We can get some air unintentionally because of the nature of those mixes where, it's all very small aggregate. And if you get the too much of a VMA or an RMA, rheology modifier, in those mixes, we tend to see the air start to creep up. So I would not want to try to control air in a UHPC mix. And if somebody wants to do that, I'd be interested to see how it turns out. I think it would be a real struggle to do that.
Very good. All right. Well, thank you, Terry. We appreciate your time today and you going through this. There was a lot of great information in this presentation, and we very much appreciate you taking the time to walk our folks through it.
Thank you.
All right. Appreciate you very much. Take care.